Okay, so today we are going to be covering a topic I know many of you are interested in. Some of you are using it for your course projects. We're going to be talking about model predictive control. This is an extremely widely used control technique, probably even more widely used than LQR. It happens to be useful for a lot of real-world applications for reasons that I will get into shortly. But today I just want to give you an introduction to model predictive control. I'm not going to make you an expert in it. I'm just going to kind of explain the general concept and give you a chance to play around with it on your own with your computers. So with that said, I've set up a code file that you can download from Canvas. So if you go to Canvas, you go to Files, Code Files. There should be a file called tank MPC. If I can see it here, tank MPC. So go ahead and download that. And we will be running it towards the end of class. Note that there is one dependency there that you might not have already. There is a library we'll be using called quadprog, which is a quadratic programming library. So we're going to be using that to solve the MPC optimization problem. If you have trouble installing it, I will come around and help you as needed later in class. So just be aware of that. Okay. Great. So let's talk a little bit about why MPC is so useful and why it's going to be useful for most of the problems that you'll be dealing with. So there's three main reasons. The first is that it handles systems with limited actuator authority. Does anyone know what I mean by limited actuator authority? Like there are constraints on the Right. So it'll handle systems where there are some constraints on the inputs that you can use to control the system. So most civil engineering problems and most real world problems will be this way. So for instance, if you have a structural system that you're trying to control, your actuator won't be able to output infinite force, right? There'll be some limitation on the amount of force that the actuator can output, and your control strategy needs to account for those limitations. Similarly, if you're working on a HVAC system or a heater system, your heater will only be able to output a limited amount of heat. It can't output a unlimited heat source, or it may be unable to input cooling to the room. So it may only be able to output heat. It may not be able to also cool the room. And so you need to account for those limitations in your actuator authority. And one important type of actuator authority that we'll be looking at in class today is for systems like reservoirs, where you may be controlling a reservoir with a valve or something like that, and you can only release a limited amount of water at a time, but the system may be subject to some kind of input disturbance that you want to avoid. So for instance, a flood wave may be coming in. You want to release water to make room for that flood wave before it arrives. So this happens all the time in real world control problems, and we need a way of accounting for it. MPC, or model predictive control, provides a way of handling those limitations on actuator authority. It's also able to accommodate just general constraints on your control problem. So for instance, you may have systems that are non-negative. For instance, if you're working with some sort of contaminant transport problem or some chemical problem, you can't have negative concentrations of contaminants. And so you may need a way to bound your state variables as well as your inputs. So MPC can do that. And finally, MPC happens to work very well for nonlinear systems. So the idea is MPC will optimize your control problem over some time horizon. What you can do is you can essentially linearize your system around that time horizon, solve the control problem for that time horizon, shift the time horizon forward, and then relinearize your system again, solve the control problem over that time horizon, and so on. And so it provides a way of handling nonlinear systems better than perhaps some of the other control techniques in this class we've looked at. Hey, are there any questions just overall conceptually on MPC before I start to move towards an example? So this example will take probably the rest of class, and we probably won't use the entire class period today. So just we can take it easy. Are there any questions about MPC before I move on? No questions? Okay, well, let's take a look at a illustrative example. Okay, so let's consider a reservoir system. This is one that we've looked at before in class. We're just going to be looking at a tank with an inlet and an outlet. Okay, so we got some inlet pipe. We've got a tank. And the tank's got an outlet pipe. You can consider this to be a long pipe. And we have some water level in the tank, which I will call H. H is the water level in the tank. We might have some inflow, which I'll call Q in. We have some outflow, Q out. And we have a couple other parameters as well. So we have the bottom area of the tank. I'll just call this A for the bottom area of the tank. I'll just write it down here, A. And finally, we have perhaps some reference water level that we're trying to track. So we want to keep the water level at this reference level. And I'll call this href. Okay, so this is the reference level that we want to track. Okay, and we've looked at this system before. So we know that the dynamical equation that describes this system is given by a mass balance as follows. So we have A times dH dt, right? This is the change in volume in the tank is equal to what? What is the change in volume in this tank equal to? Q in minus Q out, exactly right. All right, now let's say we want to track this reference water level by controlling the outflow from this outlet pipe. So the inflow is our disturbance. It's the part that we can't control. The outflow from the pipe at the bottom of the tank is what we're going to be controlling. So let's say we have a valve inside of this outlet pipe. Okay, so we have a valve in the outlet pipe, and let's say that it's a long pipe at the outlet, and therefore we can say that the maximum outflow allowed from that pipe is given by Poiseuille's law, which means that it's just going to be proportional to the water level in the tank. Okay, so our Q out is going to be less than or equal to some constant K times the height in the tank. So we've looked at this problem in class before. And also, let's just say that this valve has some sort of check valve. So we can't have negative flow. We can't have negative flow coming out of the tank. So the minimum flow that can come out of the tank is 0. All right, so this is our system. It's just a simple first order dynamical system. And we have that the parameter of the system we're controlling is this Q out parameter. So this is our control input. But our control input in this case is constrained. So it's constrained between 0 on the bottom bound, and on the upper bound it's constrained by the current state of our system, H. So let's go ahead and analyze this a bit further. So let's take a look at it in discrete time, because it's going to make it easier to work with in terms of the optimization problem. So let's discretize this system. we're just going to take that A dH by dt and let's discretize it using a discrete difference. So we'll do A times H t plus delta t minus HT over delta t, our time step, is equal to Q in t minus Q out t. So this is explicit discretization. And we can rearrange this to put ht plus delta t on the left-hand side. So we get that ht plus delta t is equal to ht, so the depth of the previous time step, plus delta t over a times q in t minus q out t. All right, so let's say we want to track href. Let's say we want to track our reference water level href. So we can set up an objective function. We can say we want to minimize the sum over all time steps. So from t equals 0 to n of ht minus href squared. So we want to minimize the squared error between our depth and the reference depth. Subject to our constraints. So subject to ht plus delta t is equal to ht plus delta t over a, qt in minus qt out, and that our q out has to be greater than or equal to 0, and q out has to be less than or equal to kht for all t. Okay, so we want to minimize the difference between the current depth and the reference depth over all time steps. What's the problem with using feedback control to achieve this objective for this problem? Kind of hinted at it towards the beginning of class. What's the problem with using feedback based on the current state of the system to try to solve this optimization problem? Sorry? So what's the problem with using a technique like PID? Why wouldn't it work very well for a problem like this? Kind of. Let me draw an illustrative example of what's possibly going to happen. And it has to do with the advantages of MPC that I alluded to towards the beginning of class. So let's say we have a plot of the flow. So this is going to be looking at both the inflow and the outflow over time. Let's say that the inflow to the system, we predict that there's going to be a big wave coming in. It's going to be a big wave coming into the system. So this is Q in. And let's say that the maximum amount of water we can let out of the system is this much. So this is the maximum amount of water we can let out at a time. So what's going to happen if we use feedback control to try to control the outflow? Sorry? Right. So if we try to use feedback control to essentially minimize the difference between H and href, we're not going to be able to, basically by the time that the control starts to act, it'll be too late because we can't let out enough water to prevent the pond from overflowing, basically, right? What we really need to do in this case is we need to plan out our control actions ahead of time. We need to release some water preemptively so that when the flood wave arrives, it doesn't overflow the reservoir. So really what we want is something that looks like this. We want to let out water preemptively, hit our maximum, and then go back down. So this would be Q out under MPC, right? If we use feedback control like LQR or full state feedback control, the system will overflow essentially because the control won't start until you've already kind of deviated from your reference, and you won't have enough actuator authority to get back to the reference once the peak of the flood wave gets really high. So you need to plan out your control actions ahead of time. Okay, are there any questions on this concept? So this is a fairly general type of problem. It occurs all over the place in controls because often you will have those constraints on your actuator authority, and you will need to plan out your control actions. Okay, so let's go ahead and just set up the full optimization problem. So let's take a look at our optimization problem. Remember that we're minimizing the sum of the squared differences between our depth and the reference depth. So this is minimization of t from 0 to n of ht minus href squared. We can express this in vector form as h minus href transpose times h minus href. So here, h is just the vector of the depths over all time steps. It's just another way of expressing this same sum here. So this is our cost function. And we also have our constraints. So we actually have both equality and inequality constraints here. So I'll write both of these. Our equality constraints essentially refer to the parameters of the system that we know. So they're the parameter of the systems that we either know or are able to predict. So for instance, we know that h naught, our depth at the first time step, is equal to some known value, h naught star. We know that qn at each time step is equal to some known value, qn star. So this is for all t in 0 to n. So these are equality constraints. When we're solving the optimization problem, we're going to assume that these are known. And generally, this qn will take the form of a prediction we have over some horizon. Okay, so that it may be a prediction of the hydrograph just based on some weather forecast or something like that. Okay, and we also have inequality constraints, which I showed before. Actually, sorry, we have one more equality constraint, which is given by the dynamical model. So ht plus delta t is equal to ht plus delta t over a times qnt minus q out t. So this is also for all t. And then we have inequality constraints, which correspond to the limitations on our control input. Okay. So our q out, sorry, I'm reversing these subscripts. Q out t has to be greater than or equal to 0 for all time steps. And q out t has to be less than or equal to k ht for all t. Now, there's many different ways to solve the MPC problem. One second, these are our constraints. So there's many different ways to solve the MPC problem. You can use just generic optimization approaches like gradient descent, for instance. The way I'm going to show you today is an efficient way, especially for systems that are linear. And that approach is called quadratic programming. So it works well if you have a convex objective function like this one. It just happens to be very fast. So what we want to do is we want to express this optimization problem as a quadratic program. So this will take the form of an objective function that looks like minimize x transpose gx, where g is symmetric and positive definite, and we're minimizing over x. So we're finding the x that minimizes this quadratic product, subject to cx is greater than or equal to b. Okay, it's where cx and b define some set of equality and inequality constraints. So we want to set up our optimization problem in this form. Okay, and that's what we're going to do. So I'm going to quickly take you through how we can do that, and then we're going to test it out in software implementation. Okay, so the first thing we got to do is we have to set up our cost function in this form. So one way we can do that is by inspecting how the state evolves over time. So basically our x vector, what we're going to be solving for is the inputs over time that drive us to meet that reference. So what we can do is we can define this G matrix to kind of express our system dynamics, which I'll show you in just a second. So first, looking at the cost function, we got to come up with a form for that G matrix. Remember that our cost function we're trying to minimize is we're trying to minimize h minus href over all time steps. So we need a way of expressing h over all time steps in terms of our known inputs. So looking at the cost function, let's look at h over all time steps. We have that h naught is known and is equal to some value h naught star. So this is a known condition. We have h1, so h at the first time step is equal to h naught plus delta t over a q in at time 0 minus delta t over a q out at time 0. h2 is much the same. It'll be h1 plus delta t over a q1 in minus delta t over a q1 out. And if we substitute this expression for h1 into this expression here, we get that h2 is equal to h naught plus delta t over a times quantity q naught in minus q naught out. Sorry. Let me actually write this as, sorry, just ignore what I just said. This will be delta t over a times q naught in plus q1 in minus delta t over a q naught out plus q1 out. And if you repeat this pattern, essentially at the nth time step, your hn will be of the form h naught plus delta t over a times the sum from k equals 0 to n minus 1 of q in at time k minus q out at time k. Okay, so this gives us a way of expressing the depth at each time step just based on the parameters of the system that we know. Okay, remember that we know q in at each time step, we know h naught, and we're solving for q out k. So those are going to be the elements of our x vector that we are solving for. Okay, so let's write this out as a matrix equation. Okay, this is going to be vector, a matrix, and another vector. Okay, so here in this left vector, I'm going to express this as our depths over each time step. So we'll have h naught, h1, h2, all the way through hn at the bottom. And this vector here, over on the right, this is our x vector in our quadratic program. So it's going to contain all of the variables that we're solving for, essentially. So it'll have h naught. It will have qn at time 0 through qn at time n minus 1. And it'll have q out at time 0 through q out at time n minus 1. So what we got to do is we have to, essentially for each row in here, we have to express our expression for h at that time step in terms of this matrix. So what's the first row of this matrix going to be? Just a 1, yep. We got a 1 right here. And the rest will be all zeros. So I'm going to partition out this matrix here just to make it a bit easier. So this is going to be all zeros. Okay, what about the next row? So what's going to be right here? If we look back on our previous slide, we have that h1 is equal to h naught plus delta t over a q naught in minus delta t over a q naught out. So what's going to be in this element here? A 1. And what about this segment here? You're going to get a delta t over a right here. And a negative delta t over a over here. And the rest of these are just going to be zeros. And similarly, the third row, you're going to have 1 delta t over a, delta t over a, 0, negative delta t over a, negative delta t over a, all zeros. Until finally, at the final row, you'll have 1, and the entire segment here is going to be delta t over a. And the final segment here is going to be negative delta t over a for the entire bottom row. All right. Okay, so we have a vector that's expressing h. We have this matrix here, and then this is x. This is the vector that we are solving for to determine these q outs over each time step. So let's go ahead and take this. I'm going to go and duplicate this slide. Okay, and let's say we want to take this and we want to re-express it as each element of this vector is now going to be h minus href. So how can we do that in terms of our matrix equation? Well, probably the easiest way is to just add another element to our x vector. So we'll put in an href here, and then I'll add another column to our matrix at the beginning equal to -1. This be -1, -1, -1, -1. And so each row of this matrix gives us an expression. Each row of this matrix equation gives us an expression for the depth at the current time step minus our reference depth. So we can call this vector here, let's call it E for the error. And this matrix here, let's call this H. So we have the E is equal to H times X. All right, so remember that what we wanted to do was we wanted to minimize the following. We want to minimize the sum of squared errors between HT and HREF squared over all time steps. So we can do that. Note that this is equal to E transpose E. Okay. Remember that E is equal to H times X. And therefore, E transpose E is equal to HX transpose HX. Okay, and what's the final expression we should get if we take this transpose? Right, X transpose H transpose HX. I wanted to ask that question because when I was grading homework 5 and 6, there were some issues with the transpose of a product. So just remember that if you're taking the transpose of a product, it flips the order of the matrices in the product, okay? Great, so this gives us our G matrix for the quadratic program. So we're halfway there. And we're going to be minimizing this expression here by selecting the elements of X. Remember, we're selecting those Q outs that will minimize this expression. Okay, finally, we need to set up constraints in the form Cx is equal to B, or sorry, Cx is greater than or equal to B. So remember that we have equality constraints. And we have inequality constraints. For our equality constraints, we remember that we have href is equal to some known href. H naught is equal to some known H naught. And Qn is equal to some known or forecasted Qn for each time step. This is Qn minus 1 n is equal to Qn minus 1 n star. So all of these quantities are a known or are basically assumed to be known or predicted. So we have a forecast of what the incoming hydrograph is going to look like. Our inequality constraints just correspond to our control actions. So we have that Q out over all time steps is greater than or equal to 0. And we have that it is less than or equal to K times H at that time step for all time steps. So this is Qn minus 1 out less than or equal to K times H n minus 1. Okay, so we have to set up a matrix equation that accounts for these inequality constraints. I'm going to go through this fairly quickly, but I wanted to show you just so that you can verify when we get to the code what it is that I am doing there. Yes.
So why don't set some constraints like the highest level to the like?
Oh, we could do that too. Yeah, we could do that too. You would just need Well, you would need another n constraints for each time step saying the water level can't be over this level. Yeah. But you could run into an infeasibility problem if you do that, just because you might encounter a wave that's too big for that problem to be solved. So that's actually a good challenge problem, and I'll add that to the end of lecture today if you want to try to implement that. Okay. Very good. Okay, so let's go ahead and set up that matrix. I just want to do this for demonstration purposes. We're going to set up the equation Cx is equal to B. And this is the last derivation I'm going to do today. Then after that, we can work with some code. All right, so this is our C matrix. This here is our X vector. And this is our B vector. Okay, so our X vector is the same as before. We'll have href, h naught. We have q in naught through q in n minus 1, and q out naught through q out n minus 1. And these rows here in our B vector correspond to the right-hand side of our constraints. So we know that href is equal to href star, for instance. We know that h naught is equal to h naught star. We know that q in is equal to q in star for each time step. So this will be q n minus 1 in star. So I'm going to go ahead and just partition this matrix here. Just as we did before. All right, so our first row, we have that href is equal to href star. So that means we're going to have just a 1 right here. And everything else is going to be zeros. For our second row, we have that h naught is equal to h naught star. So we're going to have a 1 right here. For the next segment of our matrix, we have that q in is equal to q in star for all time steps. So this is just going to be 1s along the diagonal here. And now we got to set up our inequality constraints. So we have that q out has to be greater than or equal to 0. So let's just say for these inequality constraints, this is going to be greater than or equal to. So we'll just have zeros here in our B vector. And what will the elements in this block here be? It'll just be 1s along the diagonal, right? Because we're saying that q out has to be greater than or 0 for all time steps. Okay, finally, to solve this final component of the C matrix, we need a way of expressing that q out has to be less than or equal to kh for all time steps. So we can use a similar trick as we did before. All right, so I'll come back to that in a second, but for instance, for the first time step, we need that q naught out has to be less than or equal to k times h naught. Therefore, k h naught minus q naught out has to be greater than or equal to 0. So we can go back. And we have that k times h naught. So we'll have a k right here. K times h naught minus q naught out. So we'll have a 1 right here, is greater than or equal to 0. For the next time step, we have that Q1 out has to be less than or equal to K times H1. So we can rearrange this as KH1 minus Q1 out has to be greater than or equal to 0. And if we use the same trick we did before to get KH1, this will become KH0 plus K delta T over A times Q0 in minus K delta T over A Q0 out minus Q1 out is greater than or equal to 0. Okay, so if we go back here, we will have a K right here. We will have a K delta T over A right here. And we'll have a negative K delta T over A right here and a 1 right here. So, and a 0 here. And what'll happen is, as you fill this out, you'll get a matrix that is lower triangular for each of these blocks here. So this will be K's all the way down. This here will be K delta T over A, K delta T over A on the lower diagonal. This will be negative K delta T over A, negative K delta T over A, 1. And then in the final row, I'm gonna have to stretch it out a little bit. In the final row, what you'll have is just a bottom row filled with K delta T over A. This will be negative K delta T over A. Okay, and that's it. A 0 over here. Okay, so this here, this is our C matrix. This is X, and this here is B. And that's basically it. So now what we can do is we can solve. Now we can solve our optimization problem. We want to minimize X transpose GX subject to CX is equal to B. And this will give us the outflows that will optimally meet our objective function under our constraints. Okay, I'll just show this matrix here for a second because it's not in the notes. Are there any questions on how I set this up? Cool. Well, let's go ahead and break out our computers. I've coded up an example of this problem for you. Okay, so let's take a look here. Okay, I'll just move this over here. All right. Okay, so go ahead and try opening this notebook. Fortunately, I can't control, you know what I'm gonna do? I'm gonna close open board for a second. So I can close this. Okay, so I've set up a notebook for you that implements this MPC problem. As I noted before, quadprog may not be installed on your system and it may be difficult to install, so I'll come around and help you as needed. Okay, but what we're gonna do is we're gonna initialize this thing, and actually let me restart and clear all outputs. Okay, so I'm loading my modules. I've defined a couple system parameters here. So our reference depth is going to be 10 meters. Our initial depth in the tank is going to be 10 meters. The bottom area of the tank is going to be 25 square meters. Our time step that we're going to use for the discretization is 0.1 seconds. Our linear outflow parameter is 0.25, and we're going to be running it over 100 time steps. Okay, the inflow to the system is going to be defined by this bell curve shape. So we're just going to assume a bell curve is going to be coming into the tank a bell curve shaped hydrograph, peaking at a time of about 50. So here I've defined our cost matrix, just as we did on the board. Okay, so this is how you can do that in matrix form. I've defined the constraint equation here. And this plot here, this cell here will run MPC. Before I do that, let's go ahead and just inspect what this function does. So I'm using quadprog dot solve QP. Okay, so it's going to solve a convex quadratic program of the following form. X transpose GX. Note that I've kind of just ignored this A transpose X term. That's another potential term you could add to the cost function, but I've just set A to be the zero vector here. And our constraints are going to be defined by the C transpose X is greater than or equal to B. Now note, you can specify the number of equality constraints and the number of inequality constraints. So once you specify the number of equality constraints, it'll treat the rest as inequality constraints. So let's go ahead and run this function. It computed pretty quickly. And let's go ahead and plot the output. Okay, and so here you can see the inflow and the outflow after solving the MPC problem. So note that just as I alluded to in the beginning of class, the controller lets water out of the tank preemptively before the flood wave arrives. It reaches its maximum outflow value. And then once the incoming hydrograph subsides, it starts to slowly release water again. And we can view what the water level in the tank is going to look like. So I'm going to take our control action that we computed. I'm going to put it back into the system and simulate the system under that control action and plot what it looks like. Here you can see that our reference depth is 10 meters. You can see that the tank initially lets out some water here. It gets filled back up again by the incoming wave, and then it lets water back out again after the wave subsides. So it keeps it as close as possible to that reference depth throughout the entire time period. This is essentially the best performance that you could get with the constraints that we gave it. All right, are there any questions on this implementation? So I should note that in model-predictive control, what we've done is we've essentially solved the MPC problem for one time horizon. Typically in MPC, what will happen is you'll have kind of a streaming control problem in which you take one time horizon, you solve the optimization problem for that time horizon, you implement just the first control action or the first couple control actions, and then you move the window forward to a new prediction horizon and then solve again. So this would be implementing just one of those time horizons. Typically, you just keep moving the window forward. And that helps account for a couple things. It helps account for the potential issue of your forecast changing. So like, for instance, if you have a weather forecast that's uncertain, your optimal control input for one time horizon might not be the same as when the forecast changes for your next time horizon. So it helps deal with that. It also helps deal with the nonlinearity of the system as well. So if you have a nonlinear system, the system will change depending on your control input. So if you optimize over these moving horizons, it deals with that nonlinearity by, essentially breaking it up into smaller chunks and linearizing around each time window. Okay, so just keep that in mind. That's typically how MPC is implemented as a windowed process that moves forward in time. Okay, are there any questions on MPC? All right. Oh, yes.
Can I ask a question?
Mhm.
So, with the extension of kind of the idea of observability and controllability just be feasibility in this case?
Well, controllability and observability would still exist here. Well, except they're going to be constrained, right? I would have to, I'm not exactly sure what the terminology would be for. Yeah, I'm not exactly sure what the terminology would be, but there is probably an analog to controllability and observability, those concepts for when your system is constrained. Yeah, so that's a good question. I can look that up for you. But you can kind of think of the controllability concept at least as being the same, in that is it possible to drive the system to some desired final state under a set of constraints, for instance. Cool. So with that, the first thing I want you to do is I want you to just go around and play with a couple parameters of the system, try changing around the parameters of the system and seeing what happens. You know, you might want to change the your constraints. You might want to change the maximum outflow. You might try changing the magnitude of the input wave. So first, I'm going to say, try playing around. With the notebook code, try changing around the constraints and just seeing what happens. And once you do that, I'm going to give you a couple challenge problems. Okay, the first thing I want you to do for a challenge is I want to rewrite your cost function as the LQR cost function. Okay, so I want you to try minimizing H minus href transpose times some matrix P times H minus href plus Q out transpose S Q out. So essentially rewrite the cost function to balance between the input cost and the state cost. And second, I want you to take a look for P and S. P is just make it some form of a scaled identity matrix, and S some form of a scaled identity matrix. And the second one is I want you to implement Huihai's idea. So impose a maximum water level. Figure out how to impose a maximum water level and try simulating the control strategy under that condition. You can pick either one of these challenge problems. Cool. And with that, I will come around and help if you need any help installing the software or have any questions about it. Okay, folks, it's 3:15, so I'm going to shut off the Zoom meeting. You can stay in here as long as you like. And again, I'll be having office hours at 4 today if you want to talk about your projects. I'll probably be there earlier, in fact, probably like 3:30, I'm guessing. So if you want to come talk early, you can do that too. Okay,